Tonight, we will explore a particle hiding within every single atom of your body. It is the neutron, a name you likely recognize from your earlier science classes. You were taught that it is the neutral particle residing in the nucleus, right beside the proton. While this description sounds straightforward, the reality is profoundly more complex. Here is the detail most people never learn. A neutron, when left on its own outside the protective shelter of an atom, will not survive. It is fundamentally unstable, destined to fall apart in approximately 10 minutes, unable to exist in isolation. When you begin to understand the reason for this decay, you uncover what a neutron truly is beneath its simple surface. This journey opens up one of the most captivating stories in all of physics, a narrative that weaves together quarks, the fundamental forces of nature, and the very reason that matter exists in the first place. Before we delve deeper into this mystery, if the discovery of what truly lies inside matter sparks your curiosity, a quick like or subscription greatly helps Calm Space to grow. It is a small gesture that makes a significant difference for us. Now, settle in and make yourself comfortable. Let our exploration begin. Let's start with a concept you believe you already understand: the atom. You learned about it in school, perhaps in middle or high school, where you were shown that familiar diagram. This model depicted a cluster of spheres at the center, with smaller spheres orbiting it like miniature planets. Your teacher explained that the central cluster is the nucleus, composed of protons and neutrons, while the orbiting bodies are electrons. Protons carry a positive charge, electrons a negative charge, and neutrons possess no charge at all. Their neutrality is the very origin of their name. You likely committed this picture to memory for an exam, answered a few questions, and then moved on. For most practical purposes, that mental image works well enough. It is sufficient for explaining basic chemistry and for understanding why elements on the periodic table behave as they do. It serves its purpose in our everyday lives. And yet, this image is not merely incomplete. It is almost entirely misleading about what is actually happening deep inside the atom. It is not wrong in a way that would fail you in a chemistry class, but it is wrong because it conceals something far deeper, stranger, and more beautiful than most people ever have a chance to see. Let us return to the nucleus for a moment. You were told it holds protons and neutrons, and this is true. A hydrogen atom, for instance, has one proton and no neutrons. A helium atom contains 2 of each. A carbon atom has 6 protons and 6 neutrons, while an iron atom has Vink 6 protons and Tront neutrons. The number of protons is what defines the element. If you change that number, you change the element itself. The neutrons are there as well, sitting alongside the protons, contributing mass but no electrical charge. In school, these particles were often presented as fundamental building blocks, the smallest possible pieces of the puzzle. You were taught that the atom is made of 3 particles: protons, neutrons, and electrons. For a significant period in the history of physics, the scientific community held this very same belief. The proton was discovered in 1919 by Ernest Rutherford, and the neutron followed in 1932, found by James Chadwick. The electron had been known since 1897 thanks to J.J. Thomson. For decades, these 3 particles were seen as the elementary constituents of all matter. Every star, every planet, and every person was thought to be constructed from just these 3 basic pieces. But starting in the 1950s and accelerating through the 1960s, physicists began to uncover something that troubled this tidy picture. In powerful particle accelerators, they started smashing protons and neutrons together at extraordinary energies. Instead of observing simple, solid objects, they found a chaotic aftermath. Hundreds of new particles began to appear, bearing strange names like pions, kaons, sigma baryons, and delta resonances. The list just kept expanding. Each time physicists increased the energy of their collisions, more new particles emerged from the wreckage. It was a state of pure chaos, so much so that physicists began calling it the particle zoo. None of it seemed to make any sense. If protons and neutrons were truly fundamental, then why were all these other particles being created? This bewildering complexity raised a profound question. What was really going on in the subatomic world? The answer arrived in 1964 from a physicist named Murray Gell-Mann, and independently from George Zweig. They put forth a radical proposal that protons, neutrons, and all the other particles in the so-called zoo were not fundamental at all. Instead, they were composed of even smaller things. Gell-Mann called these new particles quarks. The name was famously borrowed from a line in James Joyce's novel Times, Finnegan's Wake asterisk, 3 quarks for Muster Mark. It was a deliberately playful, almost whimsical name for what would become one of the most revolutionary ideas in the history of science. Yet, the concept behind it was profoundly serious, and it would ultimately change everything we thought we knew about the nature of matter. According to Gell-Mann's model, protons and neutrons are each made of 3 quarks, not 1, not 2, but a trio of these more elementary particles. These quarks also come in different types, which physicists refer to as flavors. In total, there are 6 flavors of quarks: up, down, strange, charm, bottom, and top. But for the purpose of understanding the neutron, we only need to concern ourselves with the 2 lightest and most common of these flavors, the up and down quarks. This simplification allows us to see the elegant structure at the heart of these familiar particles. A proton, it turns out, is made of 2 up quarks and 1 down quark. A neutron, by contrast, is composed of 2 down quarks and 1 up quark. That single substitution is the only thing that separates them. This is all it takes to shift from a positively charged proton to an electrically neutral neutron, simply swapping 1 up quark for 1 down quark. The up quark carries an electric charge of +2,3, while the down quark has a charge of -1,3. If you sum the charges inside a proton, its 2 up quarks contribute +4,3, and its single down quark adds -1,3. The total, +4,3 minus 1/3, comes to +1, which is precisely the proton's charge. For the neutron, its 2 down quarks provide a charge of -2,3, and its 1 up quark adds +2,3. The sum, -2,3 plus 2/3, is 0. This is the reason the neutron is neutral. This insight was a truly stunning revelation. The neutron's neutrality does not come from an absence of charged particles inside it. Rather, it contains charged particles whose values just happen to cancel out perfectly. The neutron, which for so long had been imagined as a simple, featureless, neutral sphere, was revealed to be a composite object. It possesses an internal structure with constituent parts and a rich, complicated interior life that remains hidden from view unless you know exactly how to look. When Gell-Mann first proposed this quark model, many physicists were deeply skeptical. To them, quarks seemed more like a mathematical trick, a convenient fiction, rather than real, physical objects. The question of whether these strange particles truly existed was one of the great challenges of the time. For a time, the very existence of quarks was a subject of intense debate among physicists. Many influential thinkers proposed they were not real objects, but simply a mathematical abstraction, a useful method for organizing the growing family of subatomic particles. This fundamental question was definitively answered between 1968 and 1969 at the Stanford Linear Accelerator Center, or SLAC. There, researchers conducted a pivotal experiment, firing beams of high-energy electrons at protons to see how they would scatter. If a proton were a single, uniform entity, the electrons would have deflected in smooth, predictable arcs. But the results showed something far more dramatic. A number of electrons ricocheted at extreme angles, as if they had struck something small, hard, and dense within the proton. The discovery was strikingly reminiscent of Ernest Rutherford's historic gold foil experiment in 1911, which had revealed the atomic nucleus. In the same way, the SLAC experiments confirmed that protons contain discrete, point-like components. These were the quarks, and they were undeniably real. For this monumental discovery, which reshaped our understanding of matter, Jerome Friedman, Henry Kendall, and Richard Taylor were awarded the Nobel Prize in Physics in 1990. With the reality of quarks established, a new and profound puzzle emerged. A neutron, for example, is composed of one up quark and two down quarks. The question was, what holds them so tightly together? After all, fundamental principles of physics suggest they should fly apart. Two of the quarks in a neutron, the two down quarks, share the same type of electrical charge and should therefore repel each other. Furthermore, these particles are confined within an astonishingly small domain, a space just 1 femtometer across. A femtometer is a quadrillionth of a meter, a distance so small it is written as a decimal point, followed by 14 zeros and a 1. At such incredibly close quarters, any repulsive force would be expected to be immense. This implies that some other force must be at play, one powerful enough to overwhelm this repulsion and bind the three quarks into a stable particle. That binding agent is the strong nuclear force, and it stands as the most powerful force in the known universe by an enormous margin. To truly grasp its sheer magnitude, it helps to compare it to the other fundamental forces. The electromagnetic force, which governs everything from the way electrons orbit an atom to the light traveling from distant stars, is approximately 100 times weaker than the strong force. And gravity, the force that anchors us to the Earth and orchestrates the dance of planets and galaxies, is weaker still by a factor of roughly 10 to the 38th power. That is a 1, followed by 38 zeros. The disparity is almost beyond comprehension. If gravity were a gentle whisper of a breeze, the strong force would be a cosmic hurricane of such intensity that it would make all of Earth's storms combined seem utterly silent. However, this immense power is matched by an equally profound strangeness. The strong force behaves in ways that are completely alien to our everyday experience. To understand its peculiar rules, we must first introduce a property called color charge. In the realm of electromagnetism, interactions are governed by electric charge, which comes in two simple types, positive and negative. Opposites attract, and like charges repel. The strong force has its own version of charge, but it is significantly more complex. Instead of just two types, there are three, which physicists have labeled red, green, and blue. It is crucial to understand that these names are merely an analogy. Quarks are not literally colored. The terms were borrowed from the system of additive primary colors because of a useful parallel. Just as combining red, green, and blue light produces white light, combining a red, a green, and a blue quark results in a particle that is color neutral. This is the fundamental reason why particles like protons and neutrons are always composed of exactly three quarks. One of each color is required to achieve a stable, color-neutral state. This requirement for neutrality is a rigid rule of nature known as color confinement. It dictates that any particle that can be observed in isolation must be color-neutral, a principle with far-reaching consequences. The particles that mediate the strong force are known as gluons. They serve a similar purpose to photons, which carry the electromagnetic force between charged particles. But this is where the comparison breaks down, revealing a critical difference. Photons themselves are electrically neutral. While they carry the force, they do not possess the charge that the force acts upon. This is why two beams of light can pass through one another, completely unaffected. Gluons, on the other hand, are fundamentally different. They are not neutral. Each gluon carries its own color charge, specifically a combination of a color and an anticolor. Because gluons are themselves colored, they interact directly with one another, constantly emitting and absorbing other gluons. This creates a dynamic of self-interaction that has no equivalent in electromagnetism, and it is the very source of the strong force's bizarre properties. This constant self-interaction of gluons results in a behavior that seems to turn physics on its head. With electromagnetism, the force between two charged particles weakens as they are pulled apart, following the predictable inverse square law. If you double the distance, the force drops to 1/4 of its initial strength. The strong force does the precise opposite. As you attempt to separate two quarks, the force binding them together does not weaken, it grows stronger. Imagine stretching an elastic band. The more you pull, the more forcefully it resists. The interaction between quarks is like that, but taken to an unimaginable extreme. As you try to pull two quarks apart, you are pumping more and more energy into the field of gluons that connects them. This field forms a kind of tube or string of energy between the quarks. As this tube is stretched, the energy stored within it increases. If you invest enough energy to stretch it far enough, a dramatic event occurs. The gluon tube snaps. But instead of freeing the quarks, the immense energy stored within the tube instantly transforms, creating a brand new quark and anti-quark pair out of pure energy. You began by trying to isolate a single quark, and you ended up creating more of them. It is a fundamental law of our universe. A single quark can never be truly alone. No matter the effort, no matter the energy expended, you will never witness a quark in isolation. It is a fundamental, unyielding rule of nature. Should you attempt to pull one free from its partners, the very energy you apply will paradoxically create new quarks, which then instantly bind with the one you sought to liberate. This principle is known as color confinement, a permanent state of imprisonment for these elementary particles. They can simply never be alone. This perplexing reality has been confirmed through countless experiments in particle accelerators across the globe, from CERN in Switzerland to Fermilab in Illinois and Brookhaven in New York. In these advanced facilities, physicists collide protons and other particles at tremendous energies. For a fleeting moment, the quarks inside are knocked loose, but they do not escape as free entities. Instead, they immediately give rise to jets of new particles, streams of protons, neutrons, and pions that spray out from the point of impact. These jets serve as the visible signature of a quark's failed attempt to break its confinement, a cascade that always results in color-neutral composite particles. No free quark has ever been detected, and the theory of the strong force, quantum chromodynamics, predicts that none ever will be. To understand this world, we must journey into the heart of a particle like a neutron, and what we find there is nothing like the simplified image many of us might imagine. The common mental picture, if one happens to think of it at all, is of three small spheres resting calmly in a tiny space, like marbles in a bag, stable, quiet, and still. That serene portrait, however, could not be more distant from the truth. The interior of a neutron is one of the most dynamic, violent, and chaotic environments in the known universe. The three quarks that define it, two down quarks and one up quark, are known as its valence quarks. Yet, they are far from being alone. The gluon field that binds them together is in a constant state of flux, with gluons being emitted and absorbed at a furious pace. Because these gluons possess sufficient energy, they can spontaneously generate quark-antiquark pairs that materialize for a moment before annihilating each other almost instantly. At any given time, a neutron contains not just three quarks, but a seething, churning ocean of so-called virtual quarks, antiquarks, and gluons, all flickering in and out of existence in a frantic dance. Physicists refer to this roiling interior as the quark-gluon sea. This hidden complexity leads to a fact that can seem almost unbelievable. The vast majority of a neutron's mass does not come from the quarks themselves. An up quark possesses a mass of only about 2.2 mega-electron volts, while a down quark has a mass of around 4.7 mega-electron volts. If you were to sum the masses of the neutron's three valence quarks, you would arrive at a total of roughly 11.6 mega-electron volts. Yet, The measured mass of a neutron is approximately 939.6 mega-electron volts. This means the quarks themselves account for barely more than 1% of the neutron's total mass. A profound question then naturally arises. Where does the other 99% of its substance come from? The answer, remarkably, is found not in matter, but in pure energy. This missing mass originates from the energy of the strong force itself, governed by Einstein's celebrated equation, E equals mc squared. It is the kinetic energy of the quarks as they race around at nearly the speed of light within their tiny prison. It is the energy contained within the countless gluons zipping back and forth between them. And it is the energy of the virtual quark-antiquark pairs constantly popping into and out of existence. All of this furious internal activity, this dynamic energy, is what manifests as the neutron's mass. As Einstein showed, energy and mass are fundamentally two sides of the same coin. The immense energy of the strong force interactions, trapped inside the neutron, is what gives it its substantial weight. This realization extends from the subatomic to the macroscopic, right up to our own existence. When you step onto a scale, the weight you see is almost entirely a measure of the binding energy within your atoms, not the intrinsic mass of the quarks that form them. You are, in a very real and tangible sense, composed mostly of confined energy rather than matter in its simplest form. The feeling of solidity in your own body, the heft of a stone in your hand, and the weight of water in a glass are all consequences of the strong force at work inside every proton and neutron of every atom. You feel heavy not because your fundamental building blocks weigh very much, they are almost massless, but because the strong force binding them is so incredibly powerful. This stands as one of the most profound insights of modern physics. The mass that we experience, the very property that gives substance and gravity to the world around us, is overwhelmingly generated by the dynamics of the strong force. It is not an inherent quality of the fundamental particles themselves. The quarks are mere wisps in this picture. The immense mass of stars, planets, mountains, and oceans is almost entirely a product of the strong force's furious energy trapped within particles so infinitesimally small that a microscope 1 billion times more powerful than any in existence would be needed just to see one. It is a humbling thought that the tangible world we know is built from something so ephemeral. Of course, this raises a further question. Where do the quarks acquire their own small, intrinsic mass? Even though it represents only a tiny fraction of a neutron's total mass, it must come from somewhere. The answer lies in a completely different mechanism, one involving the Higgs field. This is a quantum field that permeates the entirety of space. You are moving through it at this very moment. A particle's intrinsic mass is determined by its interaction with this field. The discovery of the Higgs boson in 2012 at the Large Hadron Collider at CERN was the crucial confirmation of this process. So, we have two distinct sources of mass operating at two different scales. The quarks get their small intrinsic mass from the Higgs field, while the proton or neutron gets nearly all of its mass from the energy of the strong force. There is another way to appreciate just how extraordinary the strong force is. Its incredibly short range. It operates only across distances of about 1 femtometer, which is roughly the size of a proton or neutron. Beyond that infinitesimal boundary, the force effectively vanishes into nothing. This is in stark contrast to gravity or electromagnetism, which both have an infinite range. The sun's gravitational pull holds planets in orbit across billions of miles, and electromagnetic signals can travel across the entire observable universe. The strong force, however, is confined to a space so small that you would need to line up about 1 trillion of them, side by side, just to span the width of a single atom. Despite this minuscule range of operation, the strong force is phenomenally powerful within that domain. to bind the nucleus of an atom together, overcoming the immense repulsion between protons. It simply has to be. Its incredible strength is a necessary condition for the existence of matter as we know it. The strong force holds quarks together, defying their own kinetic energy, resisting quantum effects that would spread them out, and overcoming every influence that might tear them apart. It accomplishes this with an effortless dominance. Within its domain, the strong force does not strain, it reigns completely. This also explains a curious paradox: why the most powerful force in nature has no direct effect on our daily lives. Its influence is so short-ranged that it remains entirely confined within the nucleus of an atom. You never feel the strong force because it cannot reach beyond the infinitesimally small space inside protons and neutrons. It is as if the world's most powerful engine were locked inside a box too small to be seen roaring with immense power, but on a scale so minuscule that its fury goes completely unnoticed. There is, however, something else occurring inside the neutron that is essential to understand. The quarks are not stationary. In fact, they cannot be. This is a non-negotiable decree of quantum mechanics. According to the Heisenberg uncertainty principle, one of the cornerstones of quantum physics, it is impossible to know both a particle's exact position and its exact momentum at the same time. The more precisely you define where a particle is, the less you can know about how it is moving. This is not a limitation of our instruments, but a fundamental property of nature itself, a rule that no technology could ever overcome, because quarks are confined to such a tiny space, roughly 1 femtometer across. Their positions are known with extreme precision. As a consequence, their momentum must be highly uncertain, which in practice means the quarks are moving at incredible speeds, approaching that of light. The interior of a neutron is far from calm. Its quarks race around at relativistic speeds, trapped in a prison smaller than an atom's core, constantly buffeted by gluons and surrounded by a sea of virtual particle pairs that flicker into and out of existence. It is a scene of absolute, controlled chaos, held in check only by nature's most powerful force, but chaos nonetheless. And yet, when viewed from the outside, the neutron appears perfectly serene. It presents as a single, coherent object with a well-defined mass, a specific size, no electric charge, and a quantum property known as spin. This transformation from inner pandemonium to outer composure is one of the great magic tricks of physics. How can a system of 3 quarks, caught in a maelstrom of gluons and virtual particles moving at nearly light speed, result in something that behaves like a single, simple, and stable particle? From the outside, you would never guess the turmoil held within. This brings us to another of the neutron's important characteristics. It possesses a property called spin, with a value of 1/2. This places it in a class of particles known as fermions, which also includes electrons, protons, and quarks themselves. Spin is an intrinsic quantum mechanical property that every particle has. It is not a literal physical rotation, like a spinning top, though that analogy is sometimes used to create a rough mental image. Instead, it is a fundamental quality woven into the particle at the deepest level, one that dictates how it behaves in magnetic fields and how it interacts with other particles. Because the neutron has no electric charge, you might expect it to be unaffected by magnetic fields, but it is. The neutron possesses a magnetic moment, and this discovery was one of the earliest clues that it was not a fundamental particle after all. If it were truly a simple, featureless, neutral sphere, it would have no magnetic properties. It does, however, because inside it, charged quarks are in constant motion. These moving charges generate tiny magnetic fields, and the net effect of all this internal activity gives the neutron a measurable magnetic moment. When this moment was measured experimentally, its value of approximately -1.91 nuclear magnetons beautifully matched the predictions of the quark model. The negative sign indicates that the moment points in the opposite direction of what one might naively expect, a direct consequence of the specific arrangement and motion of the quarks inside. Similarly, the neutron has a complex charge distribution, even though its total charge is zero. The interior contains regions that are slightly positive and others that are slightly negative. This internal structure tends to place the positive charge nearer to the center, while the negative charge is distributed more toward the outer edge. This arrangement has been carefully mapped using electron scattering experiments. In these studies, physicists fire electrons at neutrons and precisely measure how they deflect. The resulting scattering pattern reveals the distribution of charge inside, much like you could map the interior of a dark room by throwing tennis balls and listening for where they bounce. These experiments have confirmed the predictions of the quark model with extraordinary detail. Let us take a moment to appreciate how our understanding has evolved. We began with the simple picture often taught in school, the neutron as a neutral particle residing in the nucleus. Now we see a far more complex truth. The neutron is a composite particle, built from two down quarks and one up quark. These constituents are bound by the strong nuclear force, which is carried by gluons that also carry color charge and interact with one another. The neutron's interior is a violent, dynamic environment where quarks travel at near light speed through a sea of virtual particles and gluons. And remarkably, almost all of the neutron's mass arises not from the quarks themselves, but from the immense energy of the strong force binding them. The neutron is not a simple thing, but a complex, dynamic system held together by nature's strongest force. This intricate internal structure is not just a scientific curiosity. It is essential to the next chapter of our story. It matters because what happens to a neutron when it finds itself alone, outside the protective environment of an atomic nucleus, is a direct result of this complexity. Something fundamental goes wrong, and the neutron begins to fall apart. The specific mechanism by which it decays involves a transformation at the deepest level imaginable. One of the quarks inside the neutron changes into a different kind of quark. This transformation is governed not by the powerful strong force that holds the neutron together, but by an entirely different force of nature. Within the seemingly placid exterior of a neutron lies a universe of turmoil. It is not a simple, solid sphere, but a composite system of three quarks tethered together by the most formidable power known in nature, the strong force. This internal world is a churning sea of gluons and fleeting virtual particles. It is a place where nearly all the neutron's mass arises not from its constituent quarks, but from the immense binding energy of the strong force itself. Yet, for all its might, the strong force has a vulnerability. It cannot shield the neutron from a far more subtle influence at play in the cosmos. This other interaction, the weak force, is so faint and slow by comparison that it seems it should be inconsequential. If the strong force is a cosmic hurricane, the weak force is but a whisper. This raises a profound question. How can such a quiet, almost negligible force accomplish something the strong force is powerless to stop? It can penetrate the neutron's core, alter the very identity of a quark, and in that single act, bring about the neutron's end. To understand this process, imagine we could isolate a single neutron, removing it from the protective confines of an atomic nucleus. Picture it floating alone in the vast emptiness of space, with no other particles nearby. For a short while, nothing appears to happen. The neutron seems stable, its internal machinery of quarks and gluons operating as always. But beneath this calm facade, an invisible clock has begun to count down. A free neutron, unbound to a nucleus, is fundamentally unstable. It possesses a half-life of roughly 10 minutes and 11 seconds. This means that if we were to observe a large group of free neutrons, about half of them would have transformed after that time had passed. After another 10 minutes and 11 seconds, half of those that remained would also be gone. For any individual neutron, the precise moment of its decay is unknowable, a matter of quantum probability. But over large numbers, the statistics are firm, giving an average lifetime of about 14 minutes and 42 seconds. A span of 10 minutes may not seem like much in our daily lives. It is enough time to boil water for tea, to listen to a few favorite songs, or to walk a short distance and return. One could prepare a sandwich, enjoy it, and wash the dish in about that time. Yet, within this familiar, human-scaled interval, a lone neutron faces a 50% chance of completely disappearing. This is not a slow erosion over cosmic timescales, like the gradual decay of heavy elements deep within the Earth. Instead, this particle, a building block of nearly half the ordinary matter in the universe, falls apart in roughly the time it takes to make a cup of coffee. For something so fundamental, it is an astonishingly, almost unsettlingly, brief existence. So, what is the precise mechanism behind a free neutron's decay? To witness it, we must journey deep inside the particle, to the subatomic level of the quarks themselves, for this is where the pivotal event unfolds. As we know, a neutron is composed of one up quark and two down quarks. The decay process is initiated when one of these two down quarks undergoes a fundamental transformation. It changes its flavor, ceasing to be a down quark and instantaneously becoming an up quark. This is not a gradual shift or a slow morphing over time. It is a singular, discrete event, a point in space-time where one type of fundamental particle simply becomes another. One moment, there is a down quark with an electric charge of -1/3. The next, an up quark with a charge of +2/3 has taken its place. This sudden change of identity presents an immediate and profound challenge. One of the most sacred laws in all of physics is the conservation of electric charge. Charge cannot simply be created from nothing or vanish without a trace. The universe's books must always balance. Before the event, the down quark possessed a charge of -1/3. After the event, the newly formed up quark has a charge of +2/3. The net change is an increase of exactly +1. Where did this new positive charge originate? The answer reveals the elegance of the weak interaction. At the very instant of its transformation, the down quark emits a new particle. This is a very special and very heavy particle, known as the W- boson. It carries away precisely 1 unit of negative charge, perfectly accounting for the discrepancy. The quark's charge increases by 1, and the W- boson subtracts 1, ensuring that overall charge is perfectly conserved. The W- boson is, in fact, the messenger particle that carries the weak nuclear force itself. This concept of force carriers is central to modern physics. Just as photons transmit the electromagnetic force and gluons mediate the strong force, the weak force is conveyed by its own set of particles, the W and Z bosons. In total, there are 3 of these weak force carriers. There is the positively charged W+ boson, the negatively charged W- boson, and the neutral Z boson. In the specific case of a neutron decaying, it is the W- boson that performs this crucial task, facilitating the quark's transformation. But there is a deeply strange and counterintuitive property of the W- boson. It is extraordinarily massive. The W boson has a mass of approximately 80.4 giga-electron-volts. To give that number some context, this is about 85 times heavier than a proton, and therefore 85 times more massive than the entire neutron that just produced it. This seems like an impossible feat, akin to a small bird hatching an egg that weighs more than a full-grown elephant. How can a neutron, with a mass of only about 0.94 giga-electron-volts, create a particle that is so many times heavier than itself? This appears to be a blatant violation of the conservation of energy, a principle stating that you cannot get more energy or mass out of a system than you put in. In our classical, everyday world, this would be impossible. But the quantum realm operates by a different set of rules, and it has an extraordinary loophole. The solution to this paradox lies in the Heisenberg uncertainty principle, which we have seen before, but here it appears in a new and fascinating guise. According to a version of the uncertainty principle related to energy and time, the vacuum is not truly empty. It is a place from which energy can be borrowed, created from seemingly nothing, under one strict condition: it must be returned almost instantly. The greater the amount of energy borrowed, the more swiftly the debt must be repaid. This mechanism allows for a small loan of energy over a longer period, or a colossal one for an infinitesimally brief moment. It is through this very process of borrowing that the W- boson comes into being. A neutron, on its own, lacks the necessary energy to forge a stable W boson, so instead, the boson emerges as what physicists describe as a virtual particle. It flashes into existence on borrowed energy, lives for an unimaginably short instant, and then vanishes before the universe can call in the debt. The W boson's lifespan is a mere 3x10 to the power of -25 seconds, a number written as a decimal point, followed by 24 zeros and then a 3. In that time, even light, traveling at 300,000 kilometers per second, would traverse less than 1/10 the diameter of a single proton. The W boson is a ghost in the machine, appearing just long enough to perform its task before disappearing. So, what is the purpose of this particle's impossibly brief life? In that fleeting moment, the W- boson fulfills its entire function. It decays. It breaks apart, transforming into two new particles, an electron and an electron antineutrino. This process adheres to the fundamental law of charge conservation. The W- boson carries a negative charge, and upon its decay, this charge is perfectly transferred to the newly created electron, which has a charge of -1. The other particle, the antineutrino, is electrically neutral. In this way, the original negative charge is preserved, carried away entirely by the electron, while the antineutrino carries away energy and momentum. To appreciate this transformation, let's trace the full sequence of events. We begin with a free neutron, composed of 2 down quarks and 1 up quark. Deep within this particle, one of the down quarks emits a virtual W- boson, and in doing so, transforms itself into an up quark. The neutron's internal identity has now shifted. With 2 up quarks and 1 down quark, it is no longer a neutron, it has become a proton. Meanwhile, the W- boson, existing for only that sliver of a second, promptly decays into an electron and an electron antineutrino. The final state is a complete metamorphosis. Where there was once a single neutron, there are now 3 distinct particles: a proton, an electron, and an electron antineutrino, all flying apart. The original neutron is gone, entirely replaced by this new trio. This remarkable process is known as beta decay, or more specifically, beta minus decay. The name is a relic from the pioneering days of nuclear physics. As scientists first studied emissions from unstable atomic nuclei, they identified 3 types of radiation, which they labeled alpha, beta, and gamma. It was later discovered that what they had called beta radiation was a stream of electrons. Thus, the process that produces these electrons became known as beta decay. The minus denotes the negative charge of the emitted electron, distinguishing it from beta plus decay, which involves a positron, the electron's antimatter counterpart. For our exploration of the free neutron, however, it is beta minus decay that holds our focus. But what is the engine driving this sequence? To understand why a neutron decays this way, we must turn to the weak force. It is one of the 4 fundamental forces of nature, alongside gravity, electromagnetism, and the strong force, yet it is profoundly different. First, as its name implies, it is exceptionally weak. On the energy scales of neutron decay, The weak force is about 1,000,000 times weaker than the strong force and 1,000 times weaker than electromagnetism. This inherent weakness is why neutron decay is so slow. While 10 minutes may not seem long, in the world of particle physics, it is an eternity. Strong force interactions occur in roughly 10 to the power of -23 seconds. In contrast, the weak force operates on timescales that are billions of times longer. A free neutron surviving for 10 minutes is, in the language of the strong force, like a candle flame lasting for 1,000,000,000 years. The weak force is simply that much more deliberate. A second defining characteristic of the weak force is its incredibly limited range, even shorter than that of the strong force. While the strong force acts over distances of about 1 femtometer, the weak force's influence extends only about 1 to 3 attometers, a distance 1,000 times smaller, on the order of 10 to the power of -18 meters. This short reach is a direct consequence of the immense mass of its carrier particles, the W and Z bosons. In quantum field theory, a force's range is inversely proportional to the mass of its carrier. Because photons are massless, the electromagnetic force has an infinite range. The W and Z bosons, however, are among the most massive particles in the Standard Model. Their tremendous mass confines the weak force to a minuscule domain, requiring particles to be extraordinarily close for it to have any effect. The third, and arguably most remarkable, property is something no other force can accomplish. The weak force is the only interaction in nature capable of changing the flavor of a quark. The strong force, for all its power, cannot do this. A down quark interacting with gluons remains a down quark. The electromagnetic force is similarly limited. An electron that emits or absorbs a photon is still an electron, but the weak force is different. It can take a down quark and transform it into an up quark. This unique ability allows it to transmute one fundamental type of particle into another. It is the sole shapeshifter in the known universe, raising the question of what the cosmos would be like without this singular power. Without this mechanism, quarks would be forever locked into the flavor they were created with. The universe would be a far more static place, where matter could not transform at its most fundamental level. This unique flavor-changing capability is precisely why the weak force is responsible for so many critical processes. Without it, stars themselves could not shine. The fusion reactions that power our sun, for instance, rely on a crucial step where the weak force converts protons into neutrons. It is the subtle, yet essential, architect of change, the only force in nature that can alter the very identity of a quark. This function establishes the neutron as essential to almost every nuclear process in the universe. Focusing now on the free neutron, we've seen its decay, but what is the fundamental driver for this transformation? The explanation, as is common in physics, is rooted in energy. A neutron possesses slightly more mass than a proton. Its mass is approximately 939.565 mega-electron volts, compared to the proton's 938.272 mega-electron volts. This creates a small, yet crucial mass difference of 1.293 mega-electron volts. Although this gap is merely 1/10 of 1% of their total mass, it is sufficient to initiate the transformation. The natural world consistently trends toward the lowest available energy state, just as a ball will always roll downhill or a hot object will cool by radiating heat. In the quantum world, if a particle has a pathway to become a less massive particle, and a force exists to enable that pathway, the transformation will eventually occur. The neutron decays precisely because it is heavier than the proton, and the weak force provides the mechanism for this change. The surplus mass, the entire 1.293 mega-electron volts, is not lost. It is converted into the kinetic energy of the decay products, the electron, the antineutrino, and the proton, which recoils from the event. The electron is propelled away with an average kinetic energy of several hundred kilo-electron volts. The antineutrino carries off another fraction of the energy, and the proton recoils with a smaller amount of kinetic energy. When everything is tallied, the total energy of these resulting particles, including their rest masses, perfectly equals the neutron's original rest mass. Energy, in this intricate process, is flawlessly conserved. This seemingly minor mass difference is, however, the precise reason for the free neutron's instability, a detail on which our entire existence hinges. A difference of 1.293 mega-electron volts, when the total mass is nearly 940 mega-electron volts, is extraordinarily subtle. To draw an analogy, it's like comparing two people who each weigh about 200 pounds, but one is heavier by only a few ounces, a distinction impossible to notice visually. Nevertheless, this tiny margin determines everything. If the neutron were even fractionally lighter, tipping the mass balance the other way, the proton would become the unstable particle, while the neutron would be stable. The implications of such a reversal are nearly beyond comprehension. In a universe where protons decayed, hydrogen atoms, composed of a single proton and an electron, would be inherently unstable. The very basis of chemistry as we know it would be impossible. Stars would fail to ignite and shine in their familiar way. The cosmos would be an utterly alien place. Therefore, the simple fact that the neutron outweighs the proton by this razor-thin margin stands as one of the most profound and fortunate coincidences that permits our universe to exist. This brings us to a more profound question. What is the origin of this critical mass difference? Ultimately, both protons and neutrons are constructed from the same elementary particles, up quarks and down quarks. A proton consists of two up quarks and one down quark, whereas a neutron is made of one up quark and two down quarks. The crucial detail is that a down quark is slightly more massive than an up quark. An up quark's mass is approximately 2.2 mega-electron volts, while a down quark's is about 4.7 mega-electron volts. Since a neutron swaps one of the proton's up quarks for a down quark, it has a greater total mass from its constituent quarks. But this is only part of the explanation. The individual quark masses account for only about 1% of a proton's or neutron's total mass. The overwhelming majority of their mass originates from the tremendous binding energy of the strong force that holds the quarks together. This binding energy is also slightly different for the two particles, partly due to the electromagnetic forces at play. The quarks in a proton have a total electric charge of +1, while the quarks in a neutron sum to a neutral charge of 0. The energy required to confine positive charge in a small volume adds to the proton's mass, an effect that, on its own, would make the proton heavier. In the end, however, a delicate balance is struck, where the quark mass difference is the deciding factor. The presence of the heavier down quark is enough to make the neutron more massive overall, despite the opposing electromagnetic effect. This complex interplay yields the final mass advantage for the neutron of 1.293 mega-electron volts. Let us now consider the most elusive participant in this decay process, the antineutrino. This remarkable particle, released during neutron decay, fulfills a critical role. It is a particle of antimatter, the specific antiparticle to the electron neutrino. The neutrino family of particles is famously ethereal. For a long time, physicists theorized they were completely massless. It wasn't until experiments in the late 1990s and early 2000s that it was confirmed neutrinos have a very small mass, although its precise value is still undetermined. Current measurements suggest a neutrino's mass is less than 1 electron volt, which would make it more than 1,000,000 times lighter than an electron. Moreover, neutrinos engage with the cosmos almost solely via the weak force and gravity. They do not feel the strong force, and their lack of electric charge makes them invisible to the electromagnetic force. The only forces that affect them are gravity, which has a negligible effect on such a light particle, and the weak force, which operates over an incredibly short range of about 1/1000th of a femtometer. Consequently, neutrinos are extraordinarily non-interactive. They can pass through immense amounts of matter as if it were not there. Right now, about 65 billion solar neutrinos are passing through every square centimeter of your body every second. They travel through you and the entire Earth, with almost none of them stopping. To illustrate, a single neutrino would have a 50-50 chance of passing unscathed through a block of solid lead 1 light-year in thickness. They are true phantoms of the particle world, moving through our reality while leaving almost no sign of their presence. The history of the neutrino is particularly fascinating, as its existence was predicted by theory decades before it was experimentally confirmed. During the early 20th century, physicists investigating beta decay, the process we now understand as neutron decay, ran into a confounding problem. When they measured the decay of a neutron into a proton and an electron, the numbers for energy conservation did not balance. The established laws of physics demanded that if the decay produced only those two particles, the emitted electron must always have the same fixed amount of kinetic energy, determined by the mass difference between the parent and daughter particles. Experimental results, however, showed something different. The electron's energy varied from one decay to the next, creating a continuous spectrum. This implied that a variable amount of energy was seemingly vanishing. This puzzle led physicists to a bold hypothesis. A third undetected particle must also be emitted, carrying away the missing energy and momentum. That proposed particle was what we now call the neutrino. When physicists studied beta decay, they encountered a disturbing puzzle. The electron emerged not with a fixed energy, but with a whole spectrum of energies, from nearly zero up to a distinct maximum value. Some electrons shot out quickly, while others moved slowly. It was as if energy was simply disappearing, which created a genuine crisis in physics. The conservation of energy was a sacred principle, and if it failed at the subatomic level, the consequences for the entire field would be devastating. Some physicists, including the great Niels Bohr, seriously proposed that perhaps the law simply did not apply in the quantum realm, that the familiar rules broke down inside the atom. But in 1930, a physicist named Wolfgang Pauli proposed a far more elegant solution. He suggested that a third, undetected particle was being emitted alongside the electron. This particle, he reasoned, had to be electrically neutral, extremely light, and almost impossible to observe. It was this invisible particle, he argued, that was carrying away the missing energy. Sometimes it claimed a large portion, leaving the electron with little, and sometimes only a small fraction, leaving the electron with a lot. This sharing of energy between the electron and the mystery particle would perfectly explain the electron's variable energy, restoring order with a single, powerful idea. Pauli called his theoretical particle the neutron. However, when James Chadwick discovered the actual, much heavier neutron in 1932, that name was already taken. So, Enrico Fermi stepped in and renamed Pauli's particle the neutrino, which is Italian for little neutral one. Yet it was not until 1956, a full 26 years after its prediction, that the neutrino was directly detected. Clyde Cowan and Frederick Rhines finally observed neutrinos emanating from a nuclear reactor, confirming their existence. Rhines would later receive the Nobel Prize for this work in 1995, though Pauli never won the prize for his neutrino prediction, receiving it instead for other work. With this discovery, the full picture of neutron decay could finally be understood. A free neutron, which consists of two down quarks and one up quark, undergoes a weak interaction. During this event, one of the down quarks emits a virtual W- boson and transforms into an up quark. In that instant, the neutron becomes a proton. The virtual W- boson then decays almost immediately into an electron and an electron antineutrino. The energy released by the mass difference between the neutron and the proton is shared among the new proton, electron, and antineutrino. The electron and antineutrino fly away at high speed. The proton recoils gently, and the neutron is gone. This fundamental process is happening constantly all around us. Free neutrons are produced in nuclear reactions, particle collisions, cosmic ray interactions with our atmosphere, nuclear reactors, and supernova explosions. And every single free neutron that is created, if it is not captured by a nucleus within about 10 minutes, will decay through this exact process. A down quark becomes an up quark. A W boson appears and vanishes in a flash too brief to measure, and an electron and an antineutrino are born into the universe as a neutron dies. But here, we arrive at the key point that we must emphasize before moving forward. This is a phenomenon that happens to a times-free times neutron. This is what occurs when a neutron is alone, outside an atomic nucleus, with no other nucleons nearby. A neutron floating in empty space, unbound and solitary, is doomed. It cannot survive. The weak force will find it, reach inside it, change one of its quarks, and destroy it. 10 minutes is all the time it gets. And yet, inside your body right now, there are roughly 7 × 10 27 neutrons. That is 7 billion 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 of them. They are found inside the nuclei of the carbon, nitrogen, oxygen, calcium, iron, and every other element that makes up your flesh and bones. Those neutrons have been inside those nuclei for billions of years. Some have been bound inside stable nuclei since before the Earth was formed, since before the Sun ignited, and since the ancient stars that forged those elements exploded and scattered their contents across space. Those neutrons are not decaying. They are perfectly, completely stable. The same particle that cannot last 10 minutes alone has been sitting comfortably inside nuclei for longer than our solar system has existed. How is this possible? How can the same particle be violently unstable in one context and perfectly stable in another? The answer has to do with energy, with the environment the neutron finds itself in, and with a concept called binding energy. Understanding this difference is our next task, because the distinction between a neutron that lives for 10 minutes and one that lives for billions of years is not a difference in the neutron itself. It is a difference in where the neutron is. Context, it seems, is everything. The same particle, with the same internal structure of quarks and gluons, can be mortal or immortal, depending on whether it is alone or surrounded by others inside a nucleus. This brings us to the core of the paradox. A free neutron, left alone in empty space, decays in about 10 minutes. The weak force reaches inside, changes a down quark into an up quark, and the neutron transforms into a proton, an electron, and an antineutrino. It is destroyed. This is a particle that makes up roughly half the mass of every atom heavier than hydrogen. Yet it cannot even survive 10 minutes on its own. And still, right now, inside the atoms that make up your body, there are billions upon billions of neutrons that have been stable for longer than the Earth has existed. The neutrons in the iron atoms in your blood were forged in the core of a massive star that exploded as a supernova more than 4.5 billion years ago. Those neutrons have been sitting inside iron nuclei ever since, through the formation of the solar system, the cooling of the Earth, the origin of life, and every moment of human history. During all that time, those neutrons have been there, perfectly stable, showing no signs of decay whatsoever. It is the same particle, with the same internal structure, the same 2 down quarks and 1 up quark, the same gluons, the same churning sea of virtual particles. Everything about the neutron itself is identical, whether it is free or bound inside a nucleus. The question we must answer, then, is not about the nature of the neutron, but the nature of its home. It presents a profound cosmic paradox. In one scenario, a particle survives for only 10 minutes, while in another, it can persist for billions of years, perhaps indefinitely. How can the exact same particle be so fatally unstable in one context, yet essentially immortal in another? The solution to this puzzle is found in one of the most elegant and crucial concepts in all of physics: binding energy. To truly understand it, we must first explore what it means for particles to be bound within a composite system, as opposed to existing freely on their own. To grasp this principle, we can begin with a familiar image. Picture yourself at the base of a very deep well, hoping to climb out to the safety of ground level. To achieve this escape, you would need to expend energy. The act of climbing demands effort, which in turn requires a sufficient store of energy. If your energy is insufficient to cover the entire distance to the top, you remain trapped, unable to leave. Now, imagine someone lowers a ball to you. If you wish to throw that ball out of the well, you must impart enough force for it to overcome the well's full height. If your throw is too weak, the ball will simply fall back down, its energy inadequate for escape. This simple scenario holds a surprisingly deep parallel to the subatomic world. This same principle is at play within the heart of an atom. The protons and neutrons inside a nucleus reside in what can be described as an energy well. The immense power of the strong nuclear force has drawn them together, locking them into place, and, in doing so, has lowered their collective energy. To liberate a neutron from this arrangement, one would have to reintroduce that lost energy. You would need to provide enough of a boost to climb out of the well. The precise amount of energy required for this task is what physicists call the binding energy. It is the cost of freedom for a bound particle. This leads to a truly remarkable and counterintuitive consequence. When protons and neutrons coalesce to create a nucleus, the strong nuclear force binds them so effectively that the total mass of the finished nucleus is actually less than the sum of the masses of the individual particles that formed it. This point is so central it bears repeating. If you were to weigh a helium-4 nucleus composed of 2 protons and 2 neutrons, you would find it weighs less than 2 free protons and 2 free neutrons weighed separately. The discrepancy amounts to about 28.3 mega-electron volts. This is the binding energy, the energy that was radiated away when the 4 particles came together, and the very energy you would need to supply to pull them apart once more. This is not merely a theoretical calculation. The reduction in mass is a tangible, measurable reality. If you could place 2 free protons and 2 free neutrons on one side of an impossibly precise scale, and a single helium-4 nucleus on the other, the scale would tip in favor of the individual particles. The missing mass has not vanished, but has been converted into the energy that was released when the nucleus formed, a perfect demonstration of Einstein's famous equation, E equals mc squared. The binding energy thus manifests as a real, quantifiable decrease in mass. With this understanding, we can now return to our original puzzle of neutron decay. A free neutron is unstable because it is slightly more massive than a proton. This mass difference, a mere 1.293 mega-electron volts, is what fuels its decay. The neutron can transform into a proton because this process releases energy. Energetically speaking, the neutron is rolling downhill into the lower mass proton state, with the liberated energy carried away as the kinetic energy of an electron and an antineutrino. Within the confines of a nucleus, however, the entire energetic landscape is transformed. The neutron is now a bound particle, sitting securely in the energy well created by the strong force. Its effective energy has been significantly lowered by its binding energy. For this neutron to decay, it would have to become a proton while still remaining inside the nucleus. But the nucleus has strictly defined energy levels, specific quantum states that particles can occupy. In a stable nucleus, all the available energy states that this new proton could possibly inhabit are at a higher energy than the neutron's current state, even after accounting for the binding energy and the electromagnetic forces at play. A stable nucleus like carbon, 1,2, with its 6 protons and 6 neutrons, provides a perfect illustration of these challenges. Each neutron is held in place by a specific amount of binding energy. If one of these neutrons were to attempt to decay into a proton, the new proton would face a hostile environment. First, it would be repelled by the 6 other protons already present, as their positive charges push against each other. This electromagnetic repulsion raises the energy cost of adding another proton. Furthermore, protons and neutrons are fermions, meaning they must obey the Pauli exclusion principle, which dictates that no 2 identical fermions can occupy the same quantum state. The lower energy proton levels in carbon, 1,2, are already partially occupied, forcing the new proton into a more energetic, vacant slot. When all these factors are tallied, the secure grip of the binding energy, the electrical repulsion the new proton would encounter, and the quantum rule demanding it occupy a higher energy level, the conclusion is clear. The total energy required for the decay to proceed is far greater than the 1.293 mega-electron volts provided by the neutron-to-proton mass difference. The neutron simply does not possess enough energy to pay this tax and complete the transformation. It is, in effect, energetically forbidden from decaying. The landscape analogy becomes even more fitting. In free space, the neutron simply rolls down a gentle energetic slope to become a proton. But inside the nucleus, the binding energy has completely reshaped that terrain. The proton state, once downhill, is now at the top of a steep hill. The neutron can no longer make the journey. It is trapped in a valley of stability, unable to roll uphill. It has become stable not by changing itself, but by being placed in a new context. Herein lies the essential distinction between a particle that is free and one that is bound. A free neutron inhabits a simple energy landscape where decay into a lower mass proton is favorable. A bound neutron, by contrast, exists in a complex landscape sculpted by binding energy, electromagnetic forces, and quantum mechanical laws, where that same decay may no longer be possible. The neutron itself, its constituent quarks and gluons, its fundamental structure remains identical. What has changed is its environment, and that context makes all the difference between a fleeting life and a near-eternal one. The environment a particle finds itself in, whether it is free or bound within a larger system, is a principle that dictates its very behavior, and this concept is one of the pillars of modern nuclear physics. This idea is not exclusive to neutrons. It applies to any particle capable of existing in different energy states based on its surroundings. Yet, it is the neutron that offers the most striking illustration of this principle, because the difference in its fate is so profound. A free neutron decays in about 10 minutes, while a bound one can remain stable for billions of years. This dramatic contrast between decay and perfect stability is determined entirely by context, raising the question of what exactly creates this stabilizing environment. To understand this stability, we must look deeper into how the strong nuclear force generates binding energy. At the subatomic level, within a single proton or neutron, the strong force acts by exchanging gluons between quarks, holding them together. When we observe the nucleus as a whole, however, a more complex picture emerges. The quarks and gluons inside one nucleon do not seem to directly engage with those in a neighboring one. The powerful force that binds quarks is confined within each individual particle, and yet a residual effect of this force must exist. It is as if the force leaks out, creating a bond where a direct connection seems impossible. An elegant analogy for this phenomenon can be found in chemistry. A neutral atom, by definition, has no overall electric charge. Nevertheless, it can still attract other neutral atoms through what are known as van der Waals forces. These are residual electromagnetic effects that arise from the slight, uneven distribution of positive and negative charges within each atom. A similar principle applies to the strong force. Even though every proton and neutron is color neutral on its own, the underlying strong force extends just beyond the particle's boundary. This leakage creates an attractive residual force between adjacent nucleons, a force we call the nuclear force, and it is this very force that holds the entire nucleus together. The particles that carry this residual nuclear force are called pions, which are themselves composite particles made of a quark and an antiquark. Inside the nucleus, these pions are in a state of constant exchange between protons and neutrons. For instance, a proton might emit a pion and momentarily transform into a neutron. That pion is then absorbed by a nearby neutron, which in turn briefly becomes a proton. This exchange is a continuous and incredibly rapid dance, creating the powerful attractive force that binds the nucleons into a cohesive whole. It is a dynamic process, much like two people maintaining a connection by tossing a ball back and forth, where the act of exchange itself forms the bond. Despite its incredible strength, the nuclear force has distinct limitations crucial to its function. It is powerfully attractive at distances of around 1 to 2 femtometers, but becomes sharply repulsive at distances less than about half a femtometer. This repulsive core is essential as it prevents the nucleons from collapsing into one another and gives the nucleus its finite volume. Furthermore, the nuclear force has an extremely short range. Beyond a distance of about 2 to 3 femtometers, its strength drops to almost nothing. This means that any given nucleon within a nucleus only feels the pull of its immediate neighbors, not the nucleons on the far side. These limitations are not weaknesses, but rather the defining characteristics that shape the structure of all atomic nuclei. The short range of the nuclear force has profound implications for nuclear stability. In smaller nuclei, every nucleon is effectively a neighbor to every other one, allowing them all to feel each other's attractive nuclear force. As a result, the binding energy per nucleon tends to increase as these smaller nuclei grow in size. Helium-4, with its 2 protons and 2 neutrons, has a binding energy of about 7.1 mega-electron-volts, MeV, per nucleon. This value increases to roughly 7.7 MeV per nucleon for carbon, 1, 2, and reaches a peak of about 8.8 MeV per nucleon for iron, 5, 6. Along with nickel, 6, 2, which is slightly higher, iron, 5, 6, sits at the very summit of what physicists call the binding energy curve, representing the most stable atomic configuration in the universe. However, for nuclei larger than iron, the balance of forces begins to shift. As more protons are added to the nucleus, the electromagnetic repulsion between them intensifies. Unlike the short-range nuclear force, the electromagnetic force has an infinite range, meaning every proton in the nucleus repels every other proton, regardless of how far apart they are. In large nuclei, this cumulative electromagnetic repulsion starts to overwhelm the localized binding effect of the nuclear force. Consequently, the binding energy per nucleon begins to decrease. For example, uranium-238, one of the heaviest naturally occurring elements, has a binding energy of only about 7.6 MeV per nucleon, significantly less than iron. This cosmic tug-of-war is precisely why very heavy nuclei tend to be unstable. This interplay of forces brings us to the neutron-to-proton ratio, a critical factor determining nuclear stability. For lighter elements, the most stable arrangement typically involves an equal number of protons and neutrons. Helium-4 has 2 of each, carbon, 1-2 has 6 of each, and oxygen, 1-6 has 8 of each. This balance is logical, because the nuclear force acts almost identically between proton-proton, proton-neutron, and neutron-neutron pairs. Having equal numbers maximizes the binding energy, while the electromagnetic repulsion from the relatively few protons remains manageable. As nuclei become heavier, however, this simple balance no longer holds. The electromagnetic repulsion between the growing number of protons becomes a significant destabilizing factor. To counteract this, nature introduces extra neutrons into the mix. Neutrons contribute to the binding energy through the strong force, but because they have no electric charge, they do not add to the electromagnetic repulsion. These additional neutrons act as a kind of nuclear glue, supplying more attractive force without the cost of more repulsion. This is why heavy nuclei always have more neutrons than protons. Iron, 5,6, has 26 protons and 30 neutrons. Tin, 120, has 50 protons and 70 neutrons. And lead, 208, one of the heaviest stable nuclei, contains 82 protons and 6 neutrons. The surplus of neutrons steadily grows as the nucleus gets larger. But even this strategy has its limits. If too many neutrons are added, the nucleus becomes unstable for an entirely different reason, governed by the laws of quantum mechanics. The Pauli exclusion principle dictates that each new neutron must occupy a progressively higher energy state. Eventually, a point is reached where the highest energy neutrons are so energetic that they possess enough energy to decay into a proton, even while inside the nucleus. At this stage, the binding energy is no longer sufficient to make this transformation energetically unfavorable. When this threshold is crossed, the nucleus becomes radioactive and is primed to undergo beta decay. A neutron inside the nucleus transforms into a proton, emitting an electron and an antineutrino in the process. It is essential to grasp this point. Beta decay is not just a fate for free neutrons. It also occurs within unstable nuclei that have an excess of neutrons relative to their optimal ratio. In these atoms, the energy landscape has fundamentally shifted. The binding energy can no longer compensate for the slight mass difference between a neutron and a proton. A neutron inside the nucleus now has enough energy to transform into a proton, and so it does. An atomic nucleus can fundamentally change its identity. For a nucleus containing an excess of neutrons, this transformation occurs through a process known as beta-decay, which helps it move toward an optimal ratio of protons to neutrons. The classic illustration of this is carbon 1,4, an isotope with 6 protons and 8 neutrons. Its stable counterpart, carbon 1,2, has a balanced configuration of 6 protons and 6 neutrons. The 2 extra neutrons in carbon 1,4 render it unstable, causing it to undergo beta decay with a half-life of approximately 5,730 years. In this process, one of its neutrons converts into a proton, transforming the carbon 1,4 atom into nitrogen 1,4, which has a stable arrangement of 7 protons and 7 neutrons. This transformation, driven by the weak nuclear force, allows the system to settle into a more stable, lower energy state. This predictable decay is the foundation of radiocarbon dating. Throughout their lives, organisms continuously absorb carbon from their environment, including a small, consistent amount of carbon, 1,4, created by cosmic rays in the atmosphere. When an organism dies, this intake ceases, and the carbon, 1,4 within its tissues, begins its slow decay. By measuring the proportion of carbon, 1,4 that remains in a sample, scientists can calculate how much time has passed since the organism's death. It is a remarkable thought that this slow, steady, and predictable decay provides a clock to peer into our distant past. This powerful technique has been used to determine the age of archaeological artifacts, ancient remains, and old textiles, providing a window into the last 50,000 years, all because neutrons inside carbon 1,4 are unstable. Now, let us contrast this with the familiar carbon 1,2 nucleus, which contains 6 protons and 6 neutrons. This isotope is perfectly stable. The neutrons within it will never decay. The reason for this stability lies not in the absence of the weak force, but in the energy balance of the nucleus. The neutrons are bound so tightly that the energy landscape simply does not permit a decay to occur. They will remain locked within that nucleus for what is effectively an eternity, unless an external force manages to shatter the atom apart. This raises a crucial point in physics. The fate of a particle is often determined not by its intrinsic nature alone, but by the specific context of its environment. There is another form of instability that operates in the opposite direction, occurring in nuclei that have too many protons compared to neutrons. In such cases, a proton can transform into a neutron through a process called beta plus decay, or positron emission. This is, in essence, the reverse of what happens when a free neutron decays. An up quark within a proton emits a W plus boson and becomes a down quark, turning the proton into a neutron. The W plus boson then decays into a positron, the antimatter version of an electron and an electron neutrino. This transformation, however, can only happen inside a nucleus where the surrounding energy conditions make it favorable. A free proton, as far as all current evidence shows, is perfectly stable and does not decay, as it is lighter than a neutron and would require an input of energy to transform. To appreciate the full scope of these processes, it helps to step back. For every element, nature has a preferred nuclear configuration, a specific ratio of protons to neutrons that minimizes the total energy. If a nucleus strays from this ideal by having too many neutrons, it will undergo beta minus decay, converting neutrons into protons until the balance is restored. Conversely, if a nucleus has an excess of protons, it will undergo beta plus decay or electron capture, turning protons into neutrons. This constant adjustment is nature's way of settling its energetic accounts, always striving for the most favorable arrangement. But when a nucleus already has the ideal ratio and resides at or near its minimum energy state, neither process is favorable. The protons remain protons, the neutrons remain neutrons, and the nucleus can persist for billions of years. When plotted on a chart with proton number on one axis and neutron number on the other, the stable nuclei form a narrow curve known as the valley of stability. The nuclei that reside within this valley are the ones that have found their ideal energy state. Those that lie on either side of the valley are radioactive. Atoms with too many neutrons undergo beta minus decay, moving them toward the valley. Those with too many protons use beta plus decay or electron capture to do the same. Much like water flowing downhill, these unstable nuclei are always on a journey toward this region of calm, this valley of minimal energy. In this valley reside the approximately 252 nuclei that are considered observationally stable, meaning they have never been seen to decay. These are the survivors of the cosmos, the particles that have achieved a perfect equilibrium between the strong nuclear force, the electromagnetic force, and the quantum rules governing their arrangement. Some of these are incredibly common and form the very building blocks of our universe. Hydrogen, 1, which is just a single proton, helium, 4, carbon, 1, 2, nitrogen, 1, 4, oxygen, 1, 6, and iron, 5, 6. In every one of these stable nuclei, each individual neutron is shielded from decay by the immense binding energy that holds the entire structure together. Yet, there is something deeply fascinating about this stability. The weak force, the very agent of decay, has not disappeared. It is still present and active inside every nucleus, including the stable ones. The W boson could, in theory, still interact with the quarks inside a bound neutron. The mechanism for decay is always there, The force that would trigger it has not been switched off. The critical difference is that the overall energy conditions of the nucleus have changed. The decay is no longer energetically permitted because the nucleus's binding energy has reshaped the energy landscape. This is a subtle but profound distinction. The force for change is ever present, but the energetic opportunity for that change is not. An analogy helps to clarify this idea. Imagine a ball resting in a deep valley between two hills. Gravity, the force pulling on the ball, is constantly present. However, the ball cannot spontaneously roll up the hill without a significant input of external energy. And so, it stays put. The force exists, but it produces no effect because the energy landscape prevents the transition. The stability of the ball is not due to an absence of gravity, but to the shape of the ground it rests on. The same fundamental principle applies within the atom. This concept is truly profound. It reveals that stability is not about the absence of forces or the lack of potential decay paths. Instead, stability is a question of energy balance. A system is considered stable when there is no lower energy state that it can readily transition to. The fundamental forces are all still present, constantly probing and pushing, attempting to induce change. But if the final state would require more energy than is available, if the energy bookkeeping doesn't add up, then nothing happens. The system remains as it is. This is not just true for neutrons in nuclei. It is a fundamental principle that applies across all of physics. From the heart of an atom to the grandest cosmic structures, the story of the universe is written in the language of energy landscapes. Whether a rock sits on a hilltop or in a valley, whether a star continues burning or collapses, the outcome is always determined by the balance of energy. This simple principle governs the most profound processes in the cosmos. Consider a neutron inside a helium-4 nucleus. The binding energy holding this nucleus together is about 28.3 mega-electron volts in total, or roughly 7.1 mega-electron volts per nucleon. For that neutron to decay, it would need to become a proton. This new proton would immediately face electromagnetic repulsion from the two protons already there, and it would need to occupy a quantum state that fits the nuclear structure. When all the energetics are calculated, the final state, a nucleus with 3 protons and 1 neutron, plus an electron and an anti-neutrino, has a higher total energy than the initial state. The decay would require energy to be added, like rolling a ball uphill. It doesn't happen spontaneously, so the neutron stays. It is stable. Now, let us contrast this with the fate of a free neutron. A solitary neutron has a mass of 939.565 mega-electron volts. Its decay products are a proton with a mass of 938.272 mega-electron volts, and an electron with a mass of 0.511 mega-electron volts. The accompanying antineutrino's mass is essentially zero. The total mass of the products is about 938.783 mega-electron volts, which is less than the neutron's mass by about 0.782 mega-electron volts. There is energy left over. This means the decay releases energy, making it energetically favorable. And so, it happens. The free neutron decays. The particle's destiny, it seems, is written by its environment. Inside the stable nucleus, binding energy tips the balance the other way. Outside, there is energy to spare. Inside, there is an energy deficit. For the same neutron, made of the same quarks and gluons, and subject to the same weak force, a different energy landscape dictates a different outcome. This reveals a deep truth in physics. You cannot understand a particle's behavior without understanding its environment. Stability is not an inherent, fixed property. A neutron's stability depends entirely on the system it is part of. Strip it from a nucleus, and it dies in minutes. Leave it bound inside a stable nucleus, and it can live for the age of the universe. the particle doesn't change. The rules don't change. The forces don't change. Only the context changes, and the context is everything. There is a final, fascinating subtlety to this. In some radioactive nuclei, neutron decay does happen, but at an incredibly slow rate. Carbon, 1,4's half-life, is 5,730 years, while potassium, 4,0, has a half-life of 1.25 billion years. Some isotopes have half-lives of trillions of years, far longer than the current age of the universe. These nuclei are technically unstable. The energy balance slightly favors decay, but the process is incredibly slow because the energy available for it is so small. The decay rate depends on how much energy is available. A lot of available energy means fast decay. A tiny amount means extremely slow decay. Free neutrons have about 0.782 mega-electron volts of available energy, giving them a half-life of about 10 minutes. Some unstable nuclei, with only a few kilo-electron volts of available energy, have half-lives of billions of years. The physics is exactly the same, only the numbers change. This spectrum of stability, from perfectly stable to rapidly decaying, is all determined by the same principles we've discussed. The combination of binding energy, electromagnetic repulsion, the Pauli exclusion principle, and the neutron-to-proton ratio creates an energy landscape. It is this landscape that determines whether each nucleus is stable or unstable, and if unstable, how quickly it decays. It is all a matter of energy balance and context. And so, we have answered our question. Why can a neutron survive inside a nucleus, but not alone? Because the nucleus's binding energy changes the energy landscape. It removes the energy that would otherwise be available for decay, trapping the neutron in a state where transformation is energetically forbidden. The strong force, by binding nucleons together so powerfully, creates an environment where the weak force cannot do its work. This is one of the most beautiful examples in physics of how different forces interact. The most powerful force in nature protects the neutron from the only force that can destroy it. The strong force doesn't fight the weak force or overpower it in a direct confrontation. Instead, it reshapes the energy landscape so that the weak force has nothing to work with. It is a passive defense, not an active one. The strong force simply binds the nucleon so tightly that the weak force cannot find enough energy to cause the transformation. Within that passive defense, neutrons find safety and stability. They find, in a very real sense, immortality. This is not because they have become different particles or because a fundamental property has changed, but because they have found the right home. We now know what a neutron is. It is a composite particle made of quarks, held together by the most powerful force in nature. We know that when it is alone, it dies, as the weak force changes one of its quarks, and it transforms into a proton, an electron, and an anti-neutrino. We know that inside a stable nucleus, binding energy alters the energy landscape, protecting the neutron. The same particle is mortal in isolation, yet immortal in community. All of that is remarkable. But now, we are going to do something different. We are going to zoom out, way out. Because the story of the neutron isn't just a story about quarks and forces and binding energy. It is a story about the entire universe. It is about why the universe looks the way it does, why stars can burn, why atoms heavier than hydrogen exist, why chemistry is possible, and ultimately, why you exist at all. It all traces back to a frantic race that happened in the first few minutes after the Big Bang, a race between neutron decay and the formation of the first atomic nuclei. Let's go back to the beginning, the very beginning. About 13.8 billion years ago, the universe began in an event we call the Big Bang. In its first moments, it was unimaginably hot and dense, with temperatures in the trillions of degrees. At these temperatures, matter, as we know it, could not exist. The familiar structures of our world had not yet been forged. In the universe's very first moments, the familiar structures of matter simply did not exist. There were no stable atoms, no molecules, and not even atomic nuclei, protons or neutrons. Instead, the cosmos was a searingly hot and incredibly dense soup of fundamental particles. This primordial state was a chaotic frenzy of quarks, leptons, gluons, photons, and W and Z bosons, all colliding together at unimaginable energies. Within this maelstrom, particles were constantly being created and annihilated, a dynamic process that defies any simple description. The heat was so extreme that even the fundamental forces of nature behaved differently. At these temperatures, the electromagnetic and weak forces, which we now experience as distinct, merged into a single, unified electro-weak force. The W and Z bosons, which are incredibly massive in our cooler universe, were effectively massless because the Higgs field itself was operating under a different set of rules. It was a cosmos where the very laws of physics were alien to what we observe today. As the universe expanded, it also cooled with incredible speed. Just 1/1,000,000th of a second after the Big Bang, the temperature had fallen enough for the strong force to bind quarks together, forming the first distinct protons and neutrons. For the very first time, these cornerstones of atomic matter existed as individual particles. Yet, the universe remained unimaginably hot, with a temperature of about 1 trillion degrees Celsius. In this intense environment, protons and neutrons were not static. They were constantly converting into one another through the weak force. A proton could capture an electron and release a neutrino to become a neutron, while a neutron could decay by emitting an electron and an antineutrino to become a proton. These reactions occurred rapidly in both directions, keeping the populations of protons and neutrons in a state of dynamic equilibrium, with roughly equal numbers of each. This delicate balance, however, was destined to be broken by a subtle but crucial asymmetry. The neutron is slightly more massive than the proton, a difference of about 1.293 mega-electron volts. This means that converting a proton into a neutron requires a small but definite input of energy. When the universe was at its hottest, this energy was readily available from the thermal background. The kinetic energy of particles was so immense that this tiny mass difference was negligible. But as the cosmos continued to cool, the available thermal energy dwindled. It gradually became more difficult to transform protons into neutrons than it was to do the reverse. Slowly but surely, the equilibrium began to shift, and more neutrons started converting into protons than the other way around. A pivotal moment in this process occurred approximately 1 second after the Big Bang, when the temperature had dropped to around 10 billion degrees. At this point, the neutrinos, which had been essential mediators in the conversion reactions, decoupled from the rest of matter. The universe had expanded and cooled to a degree that neutrinos effectively ceased to interact with other particles. They began to stream freely in all directions at nearly the speed of light, and they have been traveling through the cosmos ever since, their energy diminishing as space itself expands. These ancient neutrinos still permeate all of space today, forming what scientists call the cosmic neutrino background. It is a ghostly relic from the first second of creation, one that we have not yet been able to detect directly due to the incredibly weak way neutrinos interact with everything else. The decoupling of the neutrinos had an immediate and profound impact. The rapid conversions between protons and neutrons largely froze out. The ratio of neutrons to protons became locked in at approximately 1 neutron for every 6 protons. This is known as the freeze-out ratio, and it was determined by the precise temperature at which the weak force interactions became too slow to keep pace with the universe's expansion. The fundamental ingredient list for the cosmos was now set, but this new stability introduced a critical problem for the future of matter. The neutrons were now on their own, unbound particles floating in the hot plasma of the early universe. And a free neutron is an unstable particle. A cosmic clock had started ticking. These neutrons have a half-life of about 10 minutes and 11 seconds, meaning that if left alone, they would all decay into protons. If this had happened, the universe would have been composed of nothing but protons and electrons, a cosmos of pure hydrogen. There would be no helium, no lithium, and none of the heavier elements necessary for complex chemistry, for stars as we know them, for planets, or for life. What followed was a desperate, unconscious race against time. It was a contest between the relentless decay of free neutrons and the process of nucleosynthesis, the building of atomic nuclei from protons and neutrons. The outcome of this race, which unfolded not over billions of years but in the first frantic minutes after the Big Bang, would determine the chemical composition of the entire universe for all of time to come. For nuclei to form and save the neutrons, protons and neutrons needed to bind together. The very first step on this nuclear ladder is the fusion of a proton and a neutron to create deuterium, an isotope of hydrogen. From this crucial starting point, heavier nuclei could be constructed. For instance, 2 deuterium nuclei could fuse to form helium, 3 or tritium, which in turn could combine to create helium, 4. With its 2 protons and 2 neutrons, helium, 4 is an extraordinarily stable nucleus. It represented a safe harbor, a final destination where neutrons could be locked away, permanently shielded from decay. However, there was a critical bottleneck preventing this from happening immediately. In the first few minutes, the universe was still so hot that high-energy photons, particles of light, possessed enough energy to shatter deuterium nuclei as quickly as they formed. Every time a proton and a neutron managed to stick together, a powerful photon would almost instantly collide with them and break them apart again. It was like trying to build a sandcastle while the tide continuously washes it away. This phenomenon, known as the deuterium bottleneck, stalled any significant formation of nuclei until the universe had cooled enough for deuterium to survive the constant photonic bombardment. That crucial threshold was finally reached when the temperature dropped to about 800 million degrees Celsius. The universe arrived at this point roughly 3 minutes after the Big Bang. 3 precious minutes had passed. In that time, some of the free neutrons had already decayed, causing the ratio to shift from 1 neutron per 6 protons to approximately 1 neutron for every 7. By now, only about 12 to 13% of all nuclear particles were neutrons. The rest were protons. The delay had come at a significant cost. Once the deuterium bottleneck was broken, nucleosynthesis ignited with incredible speed. In a matter of minutes, the vast majority of the remaining free neutrons were swept up and fused into helium, 4 nuclei. The process was remarkably efficient, primarily because helium, 4, is so tightly bound. Its binding energy per nucleon is so high that once it forms, it is extremely difficult to break apart again. The neutrons were captured, bound, and protected. At last, they were safe from the weak force and its power to make them decay. This brief, furious period of creation had successfully concluded, locking in the primordial elements that would one day build the stars, the galaxies, and everything we see. Within just 20 minutes of the Big Bang, the cosmic era of creation drew to a close. As the universe expanded, it cooled past the point where nuclear fusion could continue, and the furnace that forged the first elements went silent. What remained was a primordial mixture of matter with a very specific composition. By mass, approximately 75% was hydrogen, and about 25% was helium. 4. Tiny, trace amounts of deuterium, helium, 3, and lithium, 7, also peppered this cosmic soup, and that was all. These were the only elements produced in any significant quantity by the Big Bang itself. Every other element, every atom of carbon, nitrogen, oxygen, and iron that makes our world, and every fleck of gold or uranium had to be forged much later, within the hearts of stars. What makes this initial composition so extraordinary is that the 25% helium fraction was not merely an observed fact, but a profound prediction of Big Bang cosmology. During the 1960s and 1970s, physicists like Ralph Alpher, Robert Herman, and Jim Peebles meticulously calculated the physics of the early universe. Using equations on chalkboards and running simulations on early computers, they modeled the universe's expansion rate, the critical moment when the neutron-to-proton ratio was frozen, and the timing of the deuterium bottleneck. From this purely theoretical work, they predicted that about a quarter of all ordinary matter should have become helium. When astronomers later measured the helium abundance in ancient stars and distant gas clouds, places pristine and untouched by later stellar processes, they found a value of almost exactly 25%. This stunning agreement between theory and observation stands as one of the most powerful pillars of evidence for the Big Bang model. And the success of this entire calculation hinges on one fundamental constant of nature: the half-life of a free neutron. The precise rate at which neutrons decay determined the chemical fate of the universe. Let us explore for a moment why this single value matters so deeply. If the neutron's half-life had been significantly shorter, say 5 minutes instead of 10, far more neutrons would have decayed into protons by the 3-minute mark, when the deuterium bottleneck finally broke. With a much lower neutron-to-proton ratio, fewer building blocks would have been available to construct helium nuclei. The universe might have ended up with only 10% or 15% helium instead of 25%. While that may not sound like a dramatic shift, the consequences would have rippled through all of cosmic history, fundamentally altering the composition of the first stars, how they burned, and what elements they produced when they died. The great chain of stellar evolution that led to life may have been broken before it even began. On the other hand, imagine a universe where the neutron's half-life was considerably longer, perhaps 30 minutes or even an hour. In this scenario, fewer neutrons would have decayed before nucleosynthesis began. The resulting neutron-to-proton ratio would have been higher, closer to 1:6. This would have led to the formation of much more helium, possibly accounting for 30% or more of all ordinary matter. A cosmos so rich in helium would also be a difficult place for complexity to emerge. Stars forming from this gas would burn hotter and faster, living dramatically shorter lives. They might not have had the time or the right internal conditions to manufacture the careful balance of heavy elements our universe enjoys. The very potential for planet formation and the development of intricate chemistry could have been altered in ways that are incompatible with life as we know it, leaving behind a sterile cosmos. In this context, the neutron's half-life of roughly 10 minutes appears to be perfectly balanced. It is long enough for a substantial number of neutrons to survive and be captured into helium, providing the raw material for later stellar alchemy. Yet, it is also short enough to prevent an overabundance of helium, which could have derailed the stable, long-term evolution of stars. This is one of those remarkable cosmic tunings, a seemingly coincidental value for a fundamental parameter that helps make the universe habitable. This doesn't imply design, but rather suggests that if the value were different, we simply wouldn't be here to observe it. This realization leads to a profound question. Why is the neutron's half-life what it is? Why 10 minutes and not 5 or 30? The answer lies not in chance, but deep within the intricate mathematics of the weak nuclear force. The neutron's decay rate is determined by a combination of fundamental parameters from the standard model of particle physics, including the precise mass difference between the down and up quarks, the mass of the W boson, and the coupling constant of the weak interaction. These are not arbitrary numbers, but foundational properties of our physical reality. If any one of them were even slightly different, the neutron's half-life would change, and the universe as we know it might look very different. However, the neutron's cosmic significance did not end after those first 20 minutes. Even today, neutrons continue to play an essential role in the cosmos, particularly inside stars. Stars are powered by nuclear fusion, the process of merging lighter atomic nuclei into heavier ones, releasing tremendous energy. In the core of our own Sun, where the temperature is about 15 million degrees Celsius and the pressure is 260 billion times that of Earth's atmosphere, hydrogen is constantly being fused into helium through a series of reactions known as the proton-proton chain. Under these extreme conditions, protons move at such incredible speeds that they can overcome their mutual electrical repulsion and get close enough for the powerful nuclear force to take hold. Yet, the very first step in this stellar fusion chain is both the most crucial and the most difficult. Two protons must collide and fuse to form a nucleus of deuterium. The challenge is that a nucleus made of two protons, known as helium-2, is inherently unstable. The electromagnetic repulsion between the two positive charges is simply too strong for the nuclear force to overcome in that configuration, causing it to fly apart almost instantly. For the fusion to succeed, something extraordinary must happen. During the fleeting moment of collision, one of the two protons must transform into a neutron. This process, governed by the weak force, involves an up quark within the proton, changing into a down quark, an event that also emits a positron and a neutrino. This is effectively the reverse of a free neutron's decay. This transformation must occur at the exact instant the two protons are close enough for the strong nuclear force to bind them together into a stable deuterium nucleus. The probability of this event is incredibly low. Any given pair of protons in the Sun's core might wait billions of years before this reaction successfully occurs. It is this profound rarity that governs the Sun's steady, long-lasting fire, making life on Earth possible. Our Sun's steady glow is sustained by an immense number of protons, roughly 10 to the power of 57. At any given moment, a tiny fraction of these particles are, by sheer chance, undergoing a crucial reaction. This process is governed by the weak nuclear force, which makes the transformation of a proton into a neutron so remarkably slow and improbable that it acts as a cosmic bottleneck for the entire fusion process. It is this deliberate pacing that prevents our star from detonating in a single violent flash. Instead, our Sun burns with a stable, enduring fire that lasts for billions of years. The slowness of the weak force is what grants stars their longevity, and in doing so, creates the stable environments necessary for planets to form and for life itself to emerge and evolve. Without this fundamental check on fusion, the universe might be a far more fleeting and desolate place. In the final chapters of a massive star's life, neutrons begin to play an even more central role. Stars far larger than our Sun consume their hydrogen fuel rapidly, igniting a sequence of ever heavier element fusion. Helium is forged into carbon, which in turn fuses to create neon, then oxygen, and then silicon. Each successive stage demands greater temperatures and pressures, building up a core of progressively heavier elements. This process of cosmic alchemy reaches its definitive end with the element iron. Fusing elements beyond iron does not release energy, it consumes it. For a massive star, an iron core is a sign that its life as a stellar furnace is over. This inert core grows, and when it reaches a critical mass of about 1.44 times that of our Sun, it can no longer support itself against the crushing force of its own gravity. The collapse of the iron core is catastrophic, taking place in just a fraction of a second and triggering a supernova explosion. It is a cataclysm on an almost unimaginable scale, releasing more energy in a single moment than our Sun will generate over its entire 10 billion year lifespan. Amid this violent upheaval, conditions become so extreme that a tremendous flood of free neutrons is unleashed. These neutrons are immediately captured by the iron and other nuclei within the collapsing star, a process that happens so quickly it is known as the rapid neutron capture process, or R process. One after another, atomic nuclei absorb these neutrons, building up into heavier and heavier elements. This is how the cosmos forges many of its most precious materials. Gold, platinum, uranium, and thorium are all born in the heart of these stellar death throes. There is, however, a more measured pathway for creating heavy elements, known as the slow neutron capture process, or S process. This occurs within a specific class of aging stars called asymptotic giant branch stars. Here, free neutrons are produced at a much lower rate. This slower pace gives unstable nuclei time to undergo beta decay, a process where an excess neutron transforms into a proton, allowing the atom to regain stability before capturing another neutron. This patient method of atomic construction is responsible for producing approximately half of all elements heavier than iron. The other half is created by the chaotic R process that unfolds in supernovae and the mergers of neutron stars. These mergers represent some of the most spectacular and violent events observable in the universe today. Neutron stars themselves are the incredibly dense, collapsed cores left behind by massive stars not quite large enough to become black holes. Though only about 12 miles across the size of a city, they pack the mass of 1.4 to 2 suns into that compact space. The density is so extreme that a single teaspoon of this neutron star material would weigh an astonishing 4 billion tons on Earth. These objects are composed almost entirely of neutrons, squeezed so tightly that atomic nuclei have dissolved into a continuous sea of neutron matter. The gravity is equally intense, with an escape velocity from the surface reaching about 1/3 the speed of light. When two of these exotic objects spiral into one another and collide, the event sends gravitational waves rippling through the fabric of space-time. This is accompanied by a burst of gamma rays that can outshine an entire galaxy, and a cloud of neutron-rich debris is thrown out into space. Within this cloud, rapid nucleosynthesis occurs, forging a vast quantity of heavy elements and scattering them across the cosmos. In 2017, astronomers made scientific history by detecting the gravitational waves from such a collision, an event designated GW170817. Subsequent observations of the light from this merger confirmed that these events are indeed cosmic factories for heavy elements, including gold and platinum. It is a humbling realization that much of the gold found in Earth's crust may have been created billions of years ago in the collision of two neutron stars forged from the same unstable particles that cannot survive for 10 minutes alone. Closer to home, the behavior of neutrons has a profound and practical impact on nuclear technology. Within nuclear reactors, free neutrons are the essential catalysts that drive the entire process. When a uranium-235 nucleus absorbs a free neutron, it becomes intensely unstable and splits apart in a process known as nuclear fission. This rupture releases a tremendous amount of energy, around 200 million electron volts per event, along with 2 or 3 more free neutrons. These newly liberated neutrons then go on to strike other uranium nuclei, triggering more fission events in what becomes a self-sustaining chain reaction. The immense heat generated is used to boil water, create steam, spin turbines, and ultimately produce the electricity that powers our modern world. While free neutrons are inherently unstable, the time between fission events in a reactor is typically measured in microseconds, far too short for the neutron's 10-minute half-life to be a factor. The decay of neutrons also plays a vital role in the field of medical science. Certain isotopes utilized in medical imaging rely on the principles of beta decay. The electrons or positrons released during these decays can be tracked by sophisticated scanners, giving doctors a window into the workings of the human body. Positron emission tomography, or PET scanning, uses isotopes that undergo beta plus decay. The positrons emitted from these isotopes quickly encounter electrons in the body and annihilate, producing a pair of gamma-ray photons that travel in opposite directions. Surrounding detectors register these photon pairs, allowing a computer to reconstruct detailed three-dimensional images of metabolic activity. It is a profound thought that every PET scan that helps diagnose an illness owes its function to the weak force and the fundamental process of beta decay. We began this journey by considering a single, seemingly simple particle, the neutron. Yet, as we have seen, this neutral component of the atom is anything but simple. From the gentle, sustained burn of our sun to the violent creation of the heaviest elements, and from the generation of power on Earth to the diagnosis of disease within our own bodies, the neutron is a quiet but essential architect of our reality. Its story is a powerful reminder of how our universe is shaped by the intricate and often counterintuitive laws of particle physics. The neutron, for many of us, it is a particle we meet once in a classroom and then rarely think about again. A closer look, however, reveals an object of staggering complexity, a far cry from the simple sphere depicted in textbooks. Externally, it seems placid and uniform, but its interior is a turbulent maelstrom of quarks and gluons. This inherent duality also defines its very existence. An isolated neutron is remarkably fragile, decaying via the weak force in less than 10 minutes. Yet, when it is sheltered inside an atomic nucleus, the strong force provides it with a lifespan lasting billions of years. Its fate, it would seem, is not its own, but is determined completely by its surroundings. And remarkably, this single ephemeral particle, unable to survive for even 15 minutes on its own, holds the key to the whole structure of our cosmos. The precise half-life of the neutron was a crucial variable in the first moments of the universe, determining the quantity of helium that was forged during the Big Bang. This primordial ratio of elements, in turn, dictated the characteristics of the very first generation of stars. Inside those stellar furnaces, and amid the cataclysmic blasts of supernovae, the process of neutron capture was responsible for building the heavier elements that are essential for the formation of rocky planets and for life itself. There is a deep cosmic irony in the fact that the same weak force compelling a free neutron to decay is also the mechanism that allows stars to shine with stability for billions of years. Every atom of carbon in your body, every atom of oxygen you breathe, and every atom of iron in your blood is here because neutrons managed to find their way into atomic nuclei at precisely the right moments, staying there for eons to help build the periodic table. In a tangible sense, every one of us represents a continuation of this cosmic story of the neutron. The very atoms that make up your body were initially assembled within stars, where neutrons played an indispensable part. Ejected by supernovae, these same atoms traveled across the interstellar medium for millions of years before they eventually became part of the great nebula that would later collapse and form our solar system. These ancient atoms contributed to the formation of the Earth, its vast oceans, and its atmosphere. Then, over billions of years of evolution, they were woven into the fabric of life itself. And now, today, they are an integral part of you. You are made of atoms whose nuclei give shelter to these neutrons, particles that would disappear in minutes if they were ever set free. Their enduring stability being owed completely to having found the right community to belong to. There is a distinct poetry to be found in this fundamental physical principle. The neutron, it seems, is a particle that fundamentally requires a community. It is unable to persist while in isolation. It needs the embrace of other particles, bound together by the strong force, merely to continue to exist. A lone neutron is fated to undergo a rapid decay, whereas a neutron that is bound within a nucleus can achieve a form of immortality. This elementary contrast between solitude and connection, between being isolated and being part of a larger whole, serves as the very foundation from which all of the universe's elaborate complexity emerges. It points to a deep truth about structure and existence. one that is written at the subatomic scale. The next time you look down at your hand, take a moment to consider what is inside. Trillions upon trillions of neutrons. Every single one is a dynamic whirlwind of quarks and gluons, kept stable by the binding energy within its nuclear home. Each one also carries an ancient inheritance, a legacy that stretches all the way back to the first few minutes of the universe. In that primordial time, free neutrons were locked in a desperate race against their own decay, each one searching for an atomic nucleus that could offer it sanctuary before its time ran out. The ones that were successful in this cosmic race remain with us even now. They can be found in the iron that courses through your blood, the calcium that strengthens your bones, and the oxygen you are inhaling at this very moment. But what happened to all the neutrons that failed to find shelter in time? The ones that decayed during the infancy of the universe did not just disappear, they were transformed. They became the protons that would go on to form the element hydrogen. This is the same hydrogen that fills the oceans of our planet, that provides the fuel for our sun, and that is the most abundant element in the entire cosmos. In this way, the neutron's influence is truly absolute, through either its survival or its decay. By finding a home or by breaking apart, the neutron has shaped the fundamental fabric of our reality. Its narrative is, in the end, the narrative of the universe itself. And so, this story of the neutron has now become a part of your own understanding. You now know the truth of its nature, and you understand the profound reason why it is unable to endure on its own. We thank you for joining us on this exploration with Calm Space. As you settle into rest, just remember that everything in your world, every single atom and molecule, each breath you take is built upon the legacy of these fundamental particles. They are particles that cannot survive for 10 minutes alone, but which found a way to achieve permanence by coming together. Good night, and if you should ever again hear the neutron called a simple or uninteresting particle, you will know its secret and astonishing truth, that it is one of the most extraordinary objects in the entire cosmos.